Today we're going to be talking about units. You guys know through your entire scientific mathematical career, anytime you write down a number, it has to have a correct unit with it. Well, scientists have to operate by the same rules. You can't just write down 25. Well, 25 what? On this sign here, it's 25 miles per hour. But on the other sign, that's a speed limit sign as well, but that's not 30 miles per hour. I can still remember the first time that my family went on vacation to Canada, and my dad was driving on the road, and there was a sign that said 50. And I said, Dad, you can go 50 miles an hour. And it's a good thing that he didn't follow my advice, because he would have gotten a ticket. And I'm sure in Canada, getting a ticket is a little more complicated than the US. Since you're technically a foreign citizen, they might arrest you or something. So anyway, we don't put units on our speed limit signs, but that doesn't mean that it's not important to put units down. In fact, all scientists should be putting units down. This also brings us to another point about units. We all know what a mile per hour is like, or what 25 miles per hour is like. But what if I told you you could go at a speed of 0.5 parsecs per quiznip? Well, I have no idea what that means. So all units have to be in defined systems. In the US, we use the imperial system mostly. Miles, pounds, gallons, inches, these are all familiar to us. In the rest of the world, everywhere except the United States, they use the metric system. Metric system tends to be a little easier because it works in factors of 10. It's pretty easy to remember that there's 1,000 meters in a kilometer. It's much harder to remember there's 5,280 something feet in a mile. All right, the updated metric system which scientists use is actually called the international system. Believe it or not, the US government actually officially operates on this system of measurement. It's just that all of our miles are actually converted from kilometers. Some scientists, sometimes the SI system doesn't have the most easy to use units. One example of that is pressure. It's pascals is the SI unit of pressure. Scientists, chemists in particular, like to use atmospheres or torr or some other unit instead of that. For instance, if you went on a date and you gave your date 10 flowers, it probably wouldn't go over too well. So even scientists do have to kind of switch it up sometimes, not use SI all the time. All right, these are the SI base units. There's only 7 of them. Believe it or not, every single unit that we use is somehow based on these 7 units. So if you're talking about a density, that's based on mass and volume. But what's volume? Well, volume is just a cubic length. So every single unit that we use somehow boils down or is defined by these units. So what's an inch? It's 2.54 centimeters. What's a centimeter? Centimeter is 1/100th of a meter. What's a meter? Well, a meter is the base unit, and you can't define meters based on anything other than meters. So what do you define meters on? Well, first, before we get to that, we should probably talk about some other base units. Oh, by the way, the box up here means you should copy down this table. Sorry. All right, here's some derived units. So liters is actually derived from meters. Density is derived from grams and centimeters. Pressure is derived from kilograms and centimeters. So that kind of gets complicated. Even energy is actually derived from mass and distance and time and all that kind of things. So really, these are the only 7 units that everything else is defined based on. Kind of neat. All right, so your base units are defined by standards. So we said that inches is defined by centimeters, centimeters defined by meters. What's meters defined by? Well, meters are defined by a standard. It's the natural phenomenon or object which defines a base unit. Derived units are all defined based on the base units. So derived units is everything other than those 7 units. All right, so what are the standards? Well, a meter's historical definition depended on the size of the Earth. Why did we use that? Well, it's because pretty much anybody with the right equipment could measure it. And we thought it was unchanging. But that actually isn't true. We know earthquakes can kind of change the shape of the Earth. Sea levels rise and fall. Why the heck was it through Paris? That was kind of a Francophile way of doing things. So nowadays, we want our standards to be as precise as possible and to be as unchanging as possible. So the new definition of a meter is actually based on the speed of light, which anyone with the proper equipment can measure, and which we think, to the best of our knowledge, is never changing. So that's a good way to define a unit. It's something that will never change, something that anyone can measure. something that once you measure, then you can define everything based on it, because hopefully it's not changing. Seconds, we used to define second based on days, but we know days aren't exactly the best way to go. The Earth's rotation can change a little bit. Earth's rotation slows down a little bit every year. So it's not actually unchanging. It's not a standard. Now we define it based on a cesium clock. In fact, 9 billion periods of little blinks inside a cesium clock. So that's kind of neat. Again, that's unchanging, or at least we think so. The only object, remember it was, standards are all natural phenomenon or object. The only object that still acts as a standard is the kilogram standard, which is this thing. That is not a kilogram. That is the kilogram. Every single thing that weighs a kilogram on Earth is a kilogram because it has the same mass as that object. It's kind of a silly way to do things. By the way, that thing's in a vault in France. Again, the French, they seem to have a monopoly on all this unit kind of stuff. It seems a little silly, again, that we would define all weights, all masses here on Earth based on some funny little platinum iridium cylinder in a vault somewhere. But that's actually how we do things. So why is mass not defined in some sort of unchanging way like everything else? Well, it's just because we haven't come up with a better definition yet. But scientists are working on it. Anyway, anybody can actually come up with their own standard. A guy named Smoot, his MIT friends went and measured the length of this bridge in Boston. It's the MIT bridge or the Harvard bridge, depending on what school you went to. So they laid him down across the bridge one night. They were a little out of their minds, I think. But they actually measured the bridge's length in Smoots. And so George Smoot is actually the definition, is the standard. He himself is the physical object which defines the base unit Smoot. Of course, this isn't an SI unit, so don't use Smoots in class. All right, that brings us over to mass. You guys got to know that mass and weight are different things. Mass is unchanging. It depends on how much matter's in an object. Weight depends on gravity, so if you have a lower gravity, you'll have a lower weight. So actually going into orbit, going up above Earth where you become weightless, that is a weight loss technique, but it is not a mass loss technique. So when you come back down, you'll have the same weight as when you went up. Volume is just a cubic length. So if you multiply centimeters times centimeters times centimeters, you get centimeters cubed. That's a volume. 1 centimeter cubed is the same thing as a milliliter. And 1,000 centimeters cubed is the same thing as a liter. All right, this gets us to the meat and potatoes of today. We're going to be talking about metric prefixes, specifically how to convert among them. You got to be really, really, really careful with this stuff. The reason is kilo means 1,000, but doesn't milli mean 1,000 also? It's actually not true. You got to treat this a little carefully because a kilo means 1,000, but a milli doesn't mean 1,000. It means 1,000th. So again, be kind of careful with this stuff. So that means there are 1,000 meters in 1 kilometer, but there are 1,000 millimeters in 1 meter. You have to know this table. That's what the dot means. Yikes. Well, it's not as bad as you think because I already gave you a copy of this in your packet, but you do need to know the various prefixes, and you need to know what size they are, and you need to know their symbol. But you guys have seen this plenty of times before, so don't worry too much about it. All right, we're going to be talking about how to convert among metric units because if we're going to use the metric system, it probably would be nice to use it correctly. So this is how you do it. You list your metric prefixes from left to right in order. KHD, BDCM. King Henry died by drinking chocolate milk. That's a good way to remember it. You want to find the prefix that you're on and then move the dot, move the decimal, the correct number of hops to the wherever you want the prefix to be. And then let's do an example. Convert 0.05 kilograms to grams. Well, kilo is here, and grams actually has no prefix, right? It's not milligrams or decigrams or something like that. So that's the basic unit, the B in the middle. So if I'm going to convert 0.05 kilograms to grams, I'm going to be going from kilo over to the basic unit, which is 3 hops. 3 hops to the right. So now I'm going to move the dot 3 hops, 1, 2, 3, to the right. I need to put a 0 in this extra space there. So that means the actual number is 50 grams. So let's review. I just converted 0.05 kilograms to grams. It ends up 0.05 kilograms is 50 grams. So it's pretty easy to convert these things if you just move the dot. You should know that the whole King Henry died by drinking chocolate milk, kilo, hecto, deca, base, deci, centi, milli isn't all the metric prefixes. These ones on the outside, you got to know that it's actually 3 hops difference between these because they're actually different by a factor of 1,000, not a factor of 10. So you can tack them on, but unfortunately I haven't come up with a cool way of remembering it. All right, so let's do another one. Convert 5 milliseconds to kiloseconds. Well, I'm starting out at milli, and I'm going to kilo, so that's 1, 2, 3, 4, 5, 6 hops to the left. The decimal is here at the moment, even though it's not visible, it's actually there. So I'm going to be moving the decimal 1, 2, 3, 4, 5, 6 hops to the left. So that's going to be 0.00. Ooh, 3 more. 1, 2, 3. Yep. 1.0005 kiloseconds. There we go. Let's go outside. Actually, first, let's convert 20 meters to decimeters. This m is not the same as that m. Okay, this is 20 meters. There's no prefix there. There's nothing tacked on the front. So if you have an m alone, that means meters. It doesn't mean milli. So don't start at milli. You should actually start at basic unit. And you're going to d. Well, which one's d? Is it dA or d? Well, it's d. It's deci d. So all I'm going to be doing is going from base to deci. 1 hop to the right. So that's 200 decimeters. Is the same as 20 meters. All right, now let's go outside to tera, giga, mega, micro, nano, and pico. Red light has a wavelength of 650 nanometers. How many centimeters is that? Well, you start at nano, and you go to centi. But remember that that hop is actually 3 hops, and that hop is actually 3 hops, and then it's just 1 hop to the C. So we're going to be going, the decimals there right now, and we're going to be moving it 7 hops in total. 1, 2, 3, 4, 5, 6, 7 hops. 0.0000. And I should rewrite that since it looks kind of confusing. So I'm going to write 0.00065 centimeters. That's the wavelength of red light. How about that? Thanks for watching.